Assalamualaikum and good morning to our lecturer and everyone. My name is Muhammad Fikri Abdulzadin bin Hamdan. Today I will present our computer-aided engineering with my friends Akid Mizuddin bin Mustafa and Muhammad Shahir bin Bukhari. Our project title is Project Analysis of Manual Hand Drill. The project is focused on analyzing structural behavior of hand-operated drilling mechanism using CATIA and ANSYS workbench. We evaluate the original design and investigate uh, several approaches to improve its structural performance. The main objective of this project is to apply computer-aided engineering technique to evaluate and improve structural performance of manual handling. First, we developed a three-dimensional assembly using CATIA V5. The model was imported into ANSYS Workbench for structural analysis. This analysis will focus on three main indicators, which is equivalent for analysis stress, total deformation, and factor of safety. We also aim to identify critical region of the original design, particularly around crack handle and gear assembly. After identifying this region, design modification considered to improve the strength and reliability of drilling mechanism. In addition, um, the selected design was evaluated through material comparison, thermal structural analysis, and topology optimization. A hand-operated drill is a mechanical device used for manual drilling, especially when electric power is unavailable and unnecessary. During operation, the user applies force to the correct handle, and this force convert into torque, and transferred through the main gear to rotate the drill chuck and drill bit. Although the applied force may appear moderate, the crank handle and gear connection can experience bending and torsion, localized stress concentration. If design is in a decay, this condition may cause excessive deformation and permanent yielding and eventual failure. Therefore, it's important to evaluate the structural integrity of mechanism before manufacturing and physical testing. In this project, CATIA V5 was used to construct three-dimensional model, while the axis used to stimulate the loading condition and identifying the critical stress region. The scope of this project covered the modeling, analysis, and structural evaluation of the manual handling. The main task involved developing complete handle assembly in CATIA V5 and conducting static structural analysis using ANSYS. The analysis uh, focus on particularly on crack handle arm and gear mounting region because this component transfer the manual input force into the gear system. Several geometric improvements were considered, including the crank arm thickness, we adding the reinforcement and introducing the stable fillet. The performance of each module was evaluated using total deformation, equivalent von Mises stress, and factor of safety. This project also includes comparison between structural steel and stainless steel. And also we consider the thermal structural analysis and topology optimization. However, dynamic loading, vibration, fatigue, long-term weight, and manufacturing cost analysis were excluded from the current study. Finite element analysis or FEA is widely used in engineering to predict how mechanical components behave under applied load before a physical prototype is manufactured. In this project, FEA allows us to divide handle assembly into many small elements that calculate the stress deformation throughout the metal. Equivalent bond induced stress was used to evaluate the possibility of yielding, while the total deformation show displacement of the structure. The factor of safety was used to compare the calculated stress with material yield strength. Previous engineering principles show that sharp corner, holes, and small cross-section sudden geometric transition can create stress presentation. This effect may be reduced through the stable fillet, local reinforcement, or change in stiffness. Material selection is also important. Structural steel was selected as baseline material because it offers good stiffness and strength at reasonable cost. Stainless steel also considered mainly because it corrosion resistance and durability when exposed to moisture and lubricant. Finally, topology optimization was used to investigate more efficient material distinction, while thermal structural analysis was conducted to evaluate the effect of restrained thermal expansion. This concludes the introductory part of our presentation. I will now pass the presentation to uh, Shahid, who will explain our analysis procedure, geometrical model, and material properties and thermal topology optimization result.
Thank you. I'll be continuing from here. This slide presents the overall workflow used in our project. The process began with the development of the complete manual handrail assembly in CATIA. Then the model was then imported into NC's workbench. Next, structure steel was assigned as the baseline material, followed by the definition of contact condition, mass generation, fit support, and the applied mechanical load onto the assembly. The original design was first analyzed to determine its total deformation, von Mises stress, and factor of safety. The critical region identified from the original analysis was mainly located around the crank handle and gear connection. Three design modifications were considered, increasing the thickness, adding local reinforcement or ribs, and introducing a fillet at the critical transition region. After comparing the design result, further analysis were conducted. This included material comparison, thermal structure analysis, and topology optimization. Finally, all configurations were compared to determine the safest and most structurally efficient design. Now we move on to the geometrical model construction. The manual handrail model was constructed using CATIA V5 and consisted of 15 main components. These components included the frame or housing, rear handle, side handle, main gear, planetary gear or pinion gear, shafts, chuck housing, chuck jaws, and other supporting parts. The frame or housing provides the main structural support for the assembly. The rear and side handle allow the operator to hold and control the drill. The main gear and planetary gears transmit the rotation motion from the crank handle to the chuck mechanism. The chuck housing, jaws, and shaft are responsible for holding and rotating the drill bit. Among these components, the crank handle arm and its connection to the gear assembly were treated as critical regions because of the manual force is transferred through these areas. The components were modeled individually and then assembled using suitable geometric constraints to ensure correct alignment and interaction between these parts. Now we move on to the material properties of the assembly. Structural steel was used as the baseline material for the original static structure analysis. The material had a density of 7,850 kilograms per cubic meter, a young modulus of 200 gigapascals, a Poisson's ratio of zero point 0.3, a yield strength of 250 megapascals, and an ultimate tensile strength of 460 megapascals. Young's modulus represents the stiffness of the material. A higher Young modulus generally results in a lower elastic deformation under the same loading condition. The yield strength was used to calculate the factor of safety. If the equivalent stress remains below the yield strength, the material is expected to remain within the elastic region. Stainless steel was also evaluated as an alternative material. It had a Young's modulus of 193 gigapascals and a yield strength of 207 megapascal. Although the selected stainless steel had slightly lower stiffness and yield strength than structured steel, it offered better corrosion resistance, which may be useful when the handle is exposed to moisture, sweat, or lubricants.
Moving on to our methodology, we prioritize both computational efficiency and analytical accuracy in our mesh generation. We apply a global element size of 5 mm across the assembly, which local refinement focus on critical regions such as the crank handle and gear mounting interface. We utilize a tetrahedral element to discretize the complex geometry. As you can see in the table, we maintain a consistent node count below 178,000 nodes and roughly 53,000 elements across all model to ensure solver stability and reliability, structural fidelity. Next, we define our boundary conditions to replicate real world usage. Fixed support was applied to the main handle and housing of the drill by constraining all degrees of freedom. Here, we effectively simulate a secure firm grip by the user. This setup is crucial because of it allows us to accurately isolate the stress distribution and deformation occurring specifically within the rotating crank and gear assembly independent of the main rigid body. And we apply a 50 Newton concentrate force. This force was applied perpendicularly to the crank handle knob to mimic the manual effort exerting during the drilling. And this loading condition is critical for our analysis as it allows us to evaluate the structural integrity and map the von Mises distribution across the crane arm as it works to overcome the drilling resistance. Okay, my name is Muhammad Shahir bin Bukri and my metric number 24131446, and I take a part of effect of the material. So which our model constraint and loads defined, we now move to the performance analysis, starting with the baseline result, our original design. Analyzing the original design, the static structural analysis show a total deformation of approximately 0.096 millimeters. This indicate structural rigidity under our 15 newtons load. The simulation yield an equivalent von Mises stress of 85.988 MPa. When compared against the material yield strengths, this result in a factor of safety of 2.9074. This baseline confirm that the initial design is robust and provide a strong safety margin for manual tasks. To improve the performance, I'm implemented a geometry refinement by increasing the crank handle arm thickness from 1 mm to 2 mm, which is 2 millimeter. Comparing this to the original, we do see a slight increase in the total deformation and stress. It's about around 1.5 and 6% respectively. However, the design remains structurally reliable, maintaining a robust factor of safety of 2.74. This confirms that my redesign effectively handles the stress concentration while keep the tool safe for the operation. Beyond the geometry, I'm evaluate the stainless steel as an alternative to the baseline structural steel. We selected this material for its superior corrosion resistance, essential for tool exposed to gear lubricant and moisture, as well as its durability for uh, heavy duty tasks as as the table show. While there is a slight trade off in deformation compared to the 2 redesign, we still achieve a very solid factor of safety of 2.67. This demonstrates that moving to the stainless steel is a valuable part to significantly improve the tool longevity.
For thermal stress analysis, the selected handrail model was evaluated under combined mechanical and thermal loading. The reference temperature was set at 25 degrees Celsius, while the applied temperature was 50 degrees Celsius. Therefore, the model experienced a temperature difference of 25 degrees Celsius. When the temperature increased, the material attempted to expand. However, its expansion was restricted by the fit support and contact condition. This restriction generated additional thermal stress within the assembly. The simulation produced a maximum total deformation of 0.11393 millimeters. The max deformation occurred near the crank handle knob because this region was located farther from the feed support. The maximum equivalent von Mises stress reached 352.733 megapascals, with the critical stress located near the crank handle and gear connection. The minimum factor of safety was 0.70877. Since this value was below 1, the design was considered unsafe under applied thermal condition. The equivalent stress also exceeded the structural steel yield strength of 250 megapascal. This means the local yield strength or permanent deformation may occur under the simulated combined thermal and mechanical loading. The final analysis was topology optimization. Topology optimization, or structural optimization, is a numerical method used to determine where material is structurally necessary and where material may be removed or redistributed. In this analysis, a mass retention target of 90% was applied. The loading area and the main connection regions were preserved because they were required for functional load transfer. After optimization, the design was reanalyzed under the same mechanical loading and support conditions. The optimized model produced a maximum von Mises stress of 43.904 megapascal. The maximum total deformation shown in ANSYS was 0.10568 millimeters, and the factor of safety increased to 5.6942. Compared to the original design, topology optimization reduced the equivalent stress by approximately 48.94% and increased the factor of safety by approximately 95.85%. These results indicate that topology automation create a more efficient load path and reduce stress concentration. Therefore, among the reported static analysis cases, the topology optimization design achieved the best structural safety performance.
Uh, in conclusion, the effect of material has successfully utilized finite element analysis to evaluate and optimize our manual handrail. The geometric refinement of increasing the crank arm thickness to 2 combined with the transition to stainless steel has resulted in a design that is not only robust but maintain a reliable factor of safety well above 2.0. Ultimately, the stainless steel model provides the best solution by balancing mechanical longevity which environmental resistant, setting solid foundation for more durable, efficient manual tools. That's all from me. Thank you.